where we're going to start here today is with a tool that everyone who has SolidWorks has, no matter what version it is, what type of license it is, you have this object. And it's called SolidWorks SimulationXpress. It's available in every license of SolidWorks. It's a very limited analysis tool for single part stress analysis under limited conditions. The next step that people normally get into is the analysis tools that are available with SolidWorks Premium. The main component of that, and they're highlighted in blue here, the static stress analysis and also motion simulation, both of which we're going to talk about. And then our Simulation Professional tool, that introduces some other kind of modules and modes of failure for analysis. Fatigue, resonant frequency analysis, buckling predictions, basic thermal, and so on. Also introduce some other tools and functions. We're going to talk about something called Trend Tracker today. That's part of Simulation Professional. At top level, stress analysis tool breaks down two doors for us. It lets us get into nonlinear situations, and it lets us get into dynamic loading, shock, vibration, impact, those sort of things. So those are all FEA technologies, finite element analysis, all based around the same engine. If we move over to CFD, which is something we'll talk about today, we have a very robust computational fluid dynamics package, SolidWorks Flow Simulation. Comes with two add-on modules that can extend its functionality in certain industry areas. We have a sustainability tool. It's going to let you make predictions of the environmental impact of your design choices as you're designing. And the newest addition to our family is SolidWorks Plastics. It's an injection molding analysis tool. In professional, premium, and now advanced packages, depending on how much information you want. Do you want to go all the way to evaluating warp or just the mold filling and packing processes? That's kind of the landscape that we look at here when we talk about analysis in SolidWorks. So we're going to touch on some of the stuff that's in every license of SolidWorks. Motion, stress analysis, a little bit of flow, and then some general wrap-up. Okay, so that's where we're going, and go from there. So first one we'll start with here is SolidWorks SimulationXpress. SolidWorks SimulationXpress is a part level only stress analysis package. It's very limited input boundary condition availability. So we can only fix portions of the model, we can only apply forces and pressures. It only uses solid tetrahedral mesh, which means that as you're dealing with things like sheet metal or structural frames, it can be very difficult to get those to mesh. And when you look at results, you've got some limited outputs. It does include a single factor optimization tool. If you want to ask the software how thick does this plate need to be to meet a factor of safety of 3, for example, software can do that. But it is part only, single body. Now it's really in there as a bit of a teaser, right, to kind of get you interested and excited about doing stress analysis, but it uses the complete SolidWorks simulation analysis engine. So if you run an analysis in SolidWorks SimulationXpress and apply exact same conditions in SolidWorks Simulation, you'll get exactly the same answer. So let's look at a situation here. And we'll come back to this one, but let's have a little look here at a typical situation. Got a simple little bracket that I want to work with here. And, I could run analysis on it. Now, I don't have access to SolidWorks SimulationXpress if I have my simulation on. And typically, if you own any of the simulation tools, if you own SolidWorks Premium, there is no reason for you to use SimulationXpress. Okay. Now, the first thing here is, a common question we get is, I only have SimulationXpress, I have an assembly. What can I do? Then so there's a couple options. One, you can just open a part on its own and just apply the loads from the rest of the assembly. We're never going to be able to do interactions between parts in an assembly accurately in SimulationXpress, but if you just need to get an analysis done, something you can do is you can go to File, Save As, and save this assembly as a part file. Now, there's an option you really got to keep an eye on down the bottom here. You got to make sure you select all components, or else you'll just get like the surfaces on the outside of the model. Okay. So once you've done that, you save that out, close down the assembly file. Let's open up that newly created part file. And at this point in time, SimulationXpress still won't work because we have a multi-body part file. We have these 3 solid bodies in the list. So the final step you need to do to get it ready for SimulationXpress is to right-click in your bodies folder and select Combine. It's also available in Insert, Features, Combine. So that's basically going to fuse these 3 parts into one coherent solid body. So it's assuming that the interface between ball and bracket and pin is basically fused, but that's the best we can do, SimulationXpress. Now, the process for SimulationXpress, for those of you who haven't seen it before, is very, very straightforward. It's a wizard-based interface. It's going to slowly lead you through the key things that you're going to have to check out as you go through this process. Okay, so the first thing you do is identify how the object is held. The only choice we have is to rigidly fix certain faces of the model. So if we click Add a Fixture here, we can pick 1, 2, 3 locations for that. There's no control of different degrees of freedom. It's fixed or nothing, basically. Okay. In terms of loading the object, we choose between a force and a pressure. I can choose to apply a force, pick the face that I'm applying the force to. I can set it up relative to a certain vector or plane. And I've got choices between newtons and pounds force. Okay, set up as many forces and as many fixtures as I please. But there's no torque, no gravity, no thermal changes. You need the full tool to do all that. So then we select the material, extensive database available inside of the software, the complete ability to add your own material to custom libraries, just like you would in the CAD side of the thing, of the software. We can basically pick a material here, and it's going to apply the appropriate stiffness, density, and strength information. There is the ability to change the mesh resolution change basically the density of the grid that we analyze with. You may need to modify this if you've got really detailed geometry, but it's just a single control. As we'll see in the full tool, you've got multiple levels of control. So we're going to go ahead and mesh and run this analysis. All right, a couple of seconds later, we get a visual preview of how it's predicting that it'll move. Want to make sure it moves and is restrained as you expect. And then we can start looking at some data. Look at stress information, displacement information, and a model of where the factor of safety is exceeded. And so areas highlighted in red based on this prediction are looking like they'll fail. They'll exceed the yield strength for this material. Okay, we have options here to generate a Word report based on this information, or an eDrawings file that has the animation and the stress result in there. That can be really neat to share with people. And we also have the ability to get into single factor optimization. That does require a parametric model, and this conversion from assembly to part has given me a non-parametric model, basically a dumb model, so I won't be able to do that here. So all in all, it's considering you get it for nothing effectively as part of your SOLIDWORKS license, it is a moderately powerful tool, right? It uses a complete, well-tested analysis engine, but the limited inputs and the limited controls you have can make it, in certain situations particularly, not quite enough. So generally, we then talk about looking at the full analysis tool to do any sort of real analysis work on a system. Okay, we do get a few questions about it. That's really all, the process you go through to develop something in SimulationXpress. So if you're curious, go ahead and check it out. Okay. Now, next thing we get a lot of questions on is SOLIDWORKS Motion. Okay, SOLIDWORKS Motion is included as part of SOLIDWORKS Premium, and it's also included if you purchase any simulation package, Simulation Professional, Simulation Premium, the main two. And what SOLIDWORKS Motion is, it's a way to extend the general kind of articulation and movement that is inherent in SOLIDWORKS, you're developing assemblies, and add real data behind that, right? Add forces and torques and pull results off it. Okay. And so I'll look at a couple of examples here. But first of all, let's just look at the process to develop a SOLIDWORKS motion model. And so what I'm going to do here is open up a simple example here. It's a car jack. It's something that everyone's familiar with. And we might want to answer the question, if we put a portion of a car on the corner here, how much force, how much torque is going to be required to turn this handle and get it to elevate, right? If that level of torque is too high for the average human to exert, you're going to have to look at adjusting your geometry to find something that people can actually use. Now, the prerequisite for any motion analysis is that when you're right inside of SOLIDWORKS, just in the SOLIDWORKS model, the model should move in the way that makes sense to you. So you want to set up regular SOLIDWORKS mates that constrain the movement such that it moves the way you'd expect. So there's a number of hinge or concentric type mates, just connecting these mechanism elements, these bars together at their position points. And one of the main drivers of this one is a screw mate. A screw mate converts rotational motion to a linear translation. And so what this means here is if I turn the handle, it goes up. All right, so I'm just moving my mouse on the screen. But before you even start with motion, it's got to articulate in the way that you expect it to. Okay. So then we move over to motion, and SOLIDWORKS motion needs to be added in. Okay, got SOLIDWORKS motion there. And motion studies, you'll see them in any assembly. You'll see these entries at the bottom. And there's one I prepared earlier. But we'll start one from scratch. I'm just going to click down here and say Create New Motion Study. When you create a new motion study, there's 3 levels of this motion interface that you can look at. There's animation, which basically just lets you create visual movement around the model. So you want to swing the camera around, have the model rotate. All right, that's the animation level. Basic motion uses a very basic physics engine. so that if you move a part and it strikes another part, it'll push it, but there'll be no momentum transfer or anything like that. And then lastly, the full motion analysis, which starts to involve forces and torques and those sort of things. You will need motion turned on to see the third option. Otherwise, you're not going to be able to access these inputs. So the basic inputs here, this one's really simple. I want to drive this with some external force. I'm going to basically drive the handle. I'm going to drive it at 60 RPM. Okay, I've got a variety of functions that I can describe what this input looks like. I want to make sure there's a weight of the thing I'm lifting, so I want to make sure that that's being adequately captured. Okay. And so you'll see that we've got this time-based interface here with motion. It's basically, we've got the ability to control what happens against a time metric. So in the simplest situation here, you can basically tell to spin the handle for 10 seconds and show me what happened. But I can also do some interesting stuff. Say, I'm going to spin for 10 seconds, and then at this point, halfway through, I'm going to up things to 120 RPM. So I see, an acceleration occur. All right, you've got that kind of time-based control that you can adjust. But the real reason you use motion is to get numeric outputs out of it. Okay, so I can do things like ask for a result plot just from the iconography here, where I look for the the torque that the motor needs in order to drive that. So basically the input the user has to put in. What we see here is that pretty significant torque at the start when the geometry is in its least efficient position, but as we go through, it becomes easier to lift this item. And these will update with changes. If this is too much, I can then go back and look at the lengths of the members and the construction of this, rerun that motion analysis and get a new set of data out of it. Okay. You can also do things like trace the path that things take through space. Call that a displacement trace path. And if I pick a little vertex here, I find one. All right. Pretty simple path here. It's just up, down. A little bit of angle to it, but that's intentional. But if you've got complex cams and things like that, you can trace those off. And may also want to look at maybe the power used by the motor. And we can pick that motor entity. So take a look at that versus time. This is an interesting plot. As we adjust the speed, different things happen. So, the real reason you use motion is it's really adding numerics and things like momentum, inertia, contact, friction to the movement that you can articulate in basic SolidWorks. There's a couple of gotchas to look out for. For forces and loads to be truly accurate, we have to be quite specific in how we mate the model. We don't want any redundancies where two mates control the same degree of freedom of a particular component. And if you're new to motion, we do teach a one-day motion training class, available as an online class as well. But if you just want to get started, I jump into the SolidWorks tutorials. Under Design Evaluation and Simulation, there are 3 motion, regular motion tutorials in there. This one, Mate Redundancy, is a very interesting one I'd recommend. So it's worth going in and checking those out. you're interested. Now, the other most common question we get about motion is, when we run motion analysis, we get all these loading information, these pieces of loading information. All right, we can see, the reaction force at the base and the load being transferred at these pin joints. The question we get a lot is, that sounds like the information I could use in a stress analysis. How can I combine those two pieces of information? And luckily, there are two ways we can transfer information from a SOLIDWORKS motion analysis to a finite element or a stress analysis tool. So let's look at a slightly different scenario here. This is a pipe lifter. What it's designed to do is pretty straightforward. It's basically something you'd hang on the top of a forklift or a front-end loader or something like that. Big concrete pipe, the kind that make huge water mains and that sort of stuff. This thing comes in. It has these flexible arms with teeth on them. It drops down. Those run down the side, and then when it's brought back up, the friction and the geometry of this causes them to lock, pick up the pipe. Then when the front-end loader's ready to de-engage the pipe, it just needs to drop it again onto the ground, and it'll de-engage. So it's pretty nice and simple. All you need to do from a loading perspective is move this up and down in order to get it to engage. And so we actually have a motor in motion that moves this up and down in a nice, smooth, sinusoidal motion. We've got 3D contact expressed between the arms and the pipe, so that when they come together, they run on each other, and there's friction associated with it. So when we pick it up, it's great. So that's good information, right? We got a visual of us picking this pipe up. I can pull up information like how much load, how much force is required to lift the object. All right, we can see this relatively low load when you're just holding the lifter itself, but as soon as you engage the pipe, significant load required there. And so we have that force information, and we could just go take that force level, whatever it is, and go type it in to a stress analysis. That would work. But we can integrate a little deeper, and there's two ways we can do it. The first one here is what I've heard called stress recovery. And it's basically an integration between the analysis portion and the motion portion. I'm just going to try reloading this to see if I can get these results in place. I was just running this before we started, so see if we can get these results loaded. Maybe not. Okay, so the way this works is you basically come in here and say, I want to set up one of these parts or a number of these parts to be analyzed for stress. Say I want to modify, I want to look at this part here, I want to see what stress it carries across the entire motion, and that identifies this part as being something that's interesting. Okay. What we then do is we hit the button to calculate simulation results. And what happens for every frame of this analysis, it looks at the forces within this component, applies a stress analysis based on those forces, and colors the result. Okay, so it's basically going to step through the analysis, figure out the forces, and color the stress run a stress analysis and color the stress. And what it looks like when it's finished, I'll show you a short video here, is it's just a short AVI of what it looks like. Repeat this here. Basically, you see a visual coloring of the object as it runs through the analysis frame. So I get this object, relatively low stress, it's all blue, and then as it starts picking the object up, see that color come through. Right? And it's very visually appealing. The downside of this approach is that other than the view I'm looking at right now, I have no other post-processing options. Right? I can't get in and look at pick a point on the model to see the specific stress there. I cannot, I can't change to look at different factors of stress, look at principal stresses or anything like that. Right? It's very visually appealing, gives you some great animations. It's hard to get real data out of it. But it is the tightest integration between those elements. All right, so it's going to animate your stress results live inside of Motion, but other than the animation, there's not much you can do with it. Okay. The other approach we have is more of a manual process, and what we could do with this one is I can look at this and say, well, my worst case stress or worst case load, pretty sure it's going to happen right around here, right? That's the peak in my load chart where the object's carrying the most load. That's going to happen at 6 seconds. As I hover over, it gives me that nice update there. So what I can do is go to the simulation menu. You need to have simulation turned on. Go to import motion loads and say, I want to look at the lifter component. I want to see what happens at time equals 6 seconds. Go ahead and import that information for me into the file. And it looks a lot like nothing happens. This is often where people are going to bail out of here. But what it's done is it has loaded a new analysis study into this particular file. Right? This analysis study includes these weird-looking remote load variables, but these are the loads transferred at every connection point that this part has with other things in the motion analysis. We can assign materials to it. We can even apply other loads if we wish to. But this is basically the loading at a particular snapshot in time. We go off and run this item. We get a picture of the stress situation at that point in time. And the beauty of this is that we have complete variability in all the analysis tools we're used to. If I want to look at principal stresses, I can do that. If I want to pull a value off at a couple of points, I can do that. If I want to change the thickness of the part and run these same loads on it again, nothing stopping me from doing that. So you've got that complete kind of stress analysis capability if you do a manual transfer of loads from one point in time. So we do have those two approaches there, and there's pros and cons to each. This one's a lot more visual, that the real information can be limited, and this one has a wealth of information available to us. But not as visual, not as animated. I should make clear, neither method processes loading from contact or collisions. What does that mean on this example? It means I'm unable to tell you anything about, say, the loading in this arm, because this interaction is not a mated connection, it's a contact connection. Right? So, whereas this part, is connected to all the other parts by mates and motors, We're unable to identify anything about a contact. And that's just a limitation of the kinematic analysis method that motion uses. Okay, so let's pause here for a second. We've had a question come in, and please feel free to type any questions you have into the question panel and go to meeting. Next, we're going to move on to stress analysis, but there is a question. The question asks, can you do an impact analysis such as a steel ball falling from a height onto something like a glass window? In motion, we'd be able to model that movement, right? See it drop. We'd be able to make a prediction of the load transferred at the collision point, but nothing's deformable or breakable in motion, so it's going to treat everything as a rigid body. The complete way to analyze that sort of situation, an object dropping onto something else, is a nonlinear dynamic analysis, which is possible in SOLIDWORKS. That's in Simulation Premium. However, it can be very challenging. And something like that is a highly dynamic event. If that's the sort of thing you need to do every day, we'd probably recommend taking a good look at a higher end analysis tool, and would recommend something like Simulia Abacus that has explicit solvers for those sort of nonlinear dynamic events. It is possible in SOLIDWORKS, but it's the kind of thing that you got to work pretty hard to get running properly. Okay, so let's move on here, and I'm going to speed up a little bit. Let's move on to stress analysis. What do people ask us about with stress analysis? Stress analysis, one of the most common things we have is, how do I know my result is accurate? And from a code integrity point of view, that code is very rigidly tested against a number of common scenarios, against these specific benchmarks that if it doesn't give the right answer, it doesn't go out. Okay, but from a user perspective, one of the biggest controls you have over accuracy is the mesh grid that you've created. Okay. No stress result should be considered accurate until you've shown that the results don't change with increasing mesh density. What do we mean by that? Let's open up another model here. This is basically a series of plates it's going to be welded together, different positions. It's held at this back plate here, and I'm going to load it down on this hook. Okay. So, I've applied my materials, I've applied contact, and we'll talk about that in a second. I've got my fixture. It's actually a symmetric model, so I've chopped it in half and used symmetry, and I've applied my load. If I go off and run this analysis now, I get an answer. Okay, this is based on the default mesh size that we can use at a global level. I get a peak stress down on this hook here of about 83 megapascals. But if I'm questioning that, what I should always be doing is saying, what happens if I refine the mesh? I make the mesh smaller grid size. Right. Run the analysis again. And now I've got a stress of 84.1. It's gone off half a megapascal. Now, half a megapascal might be insignificant to me compared to the other errors in the model. But if I was going to do this explicitly, I'd keep refining that mesh until the value stops changing, or stops changing within a level that I'm happy with. And so you can certainly do that manually, but there are a couple of automatic tools that the software has that can be pretty useful in these situations. The first one is part of SOLIDWORKS Simulation Professional, and it's called the Trend Tracker. Here's how it works. Trend Tracker allows us to basically keep an analysis logbook of all the things we've done. Okay, it lets me to go off and say, I want to run this analysis. I'm going to run it with that mesh, default mesh size. It's going to give me the stress. 83.5, just like we got before. Then I can say, hey, keep a record of this. You right-click the top and say, I want to activate the trend tracker, and I would like to set this as my baseline. This is where I start. Okay. Creates a snapshot of all the different result plots, and then I go in and make a change. And I've learned from the last analysis that I really need to mesh in more detail in this area. I'm actually going to come in and apply a local mesh improvement called a mesh control. And that's going to refine the mesh in only that area and give me a new result. Okay, so now your value's gone up a little bit more, 86.6. But the trend tracker is keeping a history of every time I hit run, what result did I get? So we'll do it one more time, a little bit finer again, maybe 0.2 of an inch. Right, so I'm really analyzing that portion of the model in explicit detail. And see the values continuing to rise. So I could keep doing this, and what I will see is that the software keeps this logbook for me. Right? So I can go take a look at, how my displacement result is changing with each variation, or how my stress result is changing. And what you'll see as you continue to refine is that this curve will keep moving until it settles down at a stable value. And that's the true stress, the true prediction of stress for a given model. If you don't use this trend tracker, you effectively got to keep writing down each result you get on a piece of paper and see how it's progressing. Whereas this allows you to keep it in the software. And you can also track things like design changes or model variations or adding new loads. Every time you hit run, it creates an entry in this logbook, essentially, and you can go back and review it. If you decide that something you did was a mistake, you can say, hey, that third one I took a look at, that wasn't a good idea, and it will remove it from all the graphs. So a good little function there. And I've seen people use it really effectively to prove they have convergence. The other tool that we can use a lot for convergence and to make sure our mesh is good enough is something that's available in every license of simulation, so SOLIDWORKS Premium and up, and it's called adaptive meshing. Adaptive meshing is available from the properties of the study. You can go to properties and then go to the adaptive tab, and I recommend the usage of this adaptive mesh that will, and basically what this thing's doing, it's remeshing your model in areas that see high stress or high stress error is a better way of putting it. Okay, it's looking at some parameters, the expectations of stress, and it runs through a looping process whereby it refines the mesh in areas that have high stress. So let's set this thing going. It's going to start off with the default mesh density. And it's gone through 3 loops there. And nothing really seems that interesting until you go have a look at the mesh that it's created. So what's happened is automatically come in and refine the mesh around some of these high stress areas without my input. Right? So, and at the same time, it will enlarge the mesh, it'll coarsen the mesh in areas that aren't seeing significant stress error. It's almost trying to balance the mesh, put the mesh where it's needed and remove it from where it's not. And it's doing that automatically. It takes more time to process because it has to run a series of loops, but it can give you the confidence that you've got a good quality mesh and good stress convergence, or good mesh convergence before you, well, without having to do anything manually. It's a nice little tool there. It's available for solid meshes only. Okay, so we can't use it with shells or beams, but it's pretty functional. Now, one of the other most common areas that people have trouble with when they're working with simulation is contact. Okay, contact is the relationship between parts in assembly. It can either be, two parts can be bonded together or fused together, or they can have a sliding interaction where they call it no penetration. They're free to slide on top of each other. And most of the confusion that comes up is through not understanding what the software is trying to do by default. Okay? And so what the software is trying to do by default, if you start a new analysis, I'm just going to activate a version of the model here. If you start a new analysis from scratch, what the software does is it builds this thing called a global contact item. This global contact is a condition that applies to every face in the model that starts off touching. Okay, so any faces that have a touching relationship, this thing glues them together. Now you can tell the software, hey, that every face in the model that's touching is actually a sliding relationship. Or you can tell the model that, hey, I just want to delete this. I don't want you to make any assumptions out of the box, if you wish. Now, the software won't do anything automatically for faces that are not touching. So a common thing we hear people say is, I mated them together, a 1/4 inch apart to allow from a weld. Why aren't they tied together in the analysis? And stress analysis doesn't look at mates at all, by design. There's many situations you have a mate that shouldn't be a connected relationship. It only looks at where the faces are touching. Something they've given us here in SOLIDWORKS 2014 that's a great help is a contact visualization plot. It basically will highlight places in the model where you have those touching interfaces. It'll also include anything you've manually added. And so this basically lets you scan the model and find places you might have missed. So, I actually have an issue here. I don't have a relationship between my loading hook and the bottom plate because there's a physical gap there. Okay, and as there's no highlighted red interface there, I can see it visually. As this stands, this isn't going to work. Now, if we want to change something about the way contact is applied, we can override this global contact with two other types of contact. What's called component contact, which is a relationship between two parts. Right, so anywhere those two parts touch, this gets applied. And the local contact set, which is a relationship between two sets of faces, and for that one there, it doesn't matter if they're touching or not. So in this one here, I could say I want a component contact between here and here. And it will scan for touching faces between those two components and apply contact condition appropriately. In SOLIDWORKS 2014, there is an option here to search for non-touching faces. So I want to find faces that are within 0.1 of an inch of each other. In testing for this particular presentation, I wasn't able to get that one working as I really expect it to. This is also available on the global contact. I'm on SP1. I'm going to try SP2 afterwards. But be aware that's there, but just kind of interrogate what's happening with it as you go through. But my preferred method of applying individual contacts is to use this contact set choice and select the face pairs that are interacting together. All right, so I've just applied a connection between that, and I can go visualize that in this contact visualization plot. So I now have a red connection between those two elements. If I was to run a mesh, create a mesh, and check this box to include solver-generated contacts, it'll actually show me which mesh cells are connected to which can be pretty interesting to view as well. Okay, so there's some new tools there. Contact visualization and non-touching face pairs for global contact and component contact are new for 2014. The visualization especially has already helped me troubleshoot some pretty complex models. So I'm pretty excited about using that. Okay. Common question we get is, what options should I set in SOLIDWORKS simulation? Simulation options. We've got these things here. And there are some things that I'd really strongly recommend you adjust in here. But just to come back to a question here that's just come in, a question is, when I did that contact between here and here, should I split the second face so I have the exact imprint of it? The answer is the software will find the adjacent nodes, so you don't generally need to split the face on the second part. You just pick the two faces and it will map where the little part here, where it touches the big part, where it's close to the big part. And you'll see that visually if you actually run a mesh and do those contact generated options. So we're to backtrack there. Hopefully that answer that question. So here's what I recommend in the options. First one here is there's an option for the result file location. It tells the software where to put the results. Results are big, and they're useless to you as a file, right? They're useful once you post-process them through the interface, but often they can just clutter things up. If you're working on a local drive, primarily, or a data management system, I recommend choosing the option to put the results in a subfolder and call it something that's easy to search for, like results. Right? That means that when I'm going to purge analysis data I don't think I need, I can just do a search for the word results. I'm not indexed here, but it'll give me a list of all the folders, all the result folders I have. I should probably point it to my main file location and just come through and say, oh, no, I'm still doing that presentation. I need to keep that one. This one here I can delete and just purge it from one interface. It also means all those result files are put in a folder separate from the CAD files you're going to need. Okay? The only time I don't recommend doing that is if you're on a network drive. If you're on a network drive, you should always point the result files to a local fixed location. It'll run hundreds of times faster. Next one here is to run Simulation Advisor from the Command Manager. Find once you've run 2 or 3 analyses, you don't need to go through this study advisor process where it leads you through all the questions and asks everything you need to look at. But by default, if you just pick on this button, it'll take you into that interface. So it's kind of annoying. There's an option right down here to turn that off. You got to restart SOLIDWORKS before, but then when I just hit this button, I'm not taking the advisor interface. I can just go straight to a new study. That's just a little one. If you work with shell mesh a lot, or even if you don't, I'd recommend coming into the default options mesh and turn off automatic realignment of non-composite shells. That disables some secondary checking that the software does when you create a shell mesh, but often that secondary checking can take 5 to 10 times as long as the actual mesh process. Does mean you will have to go visually scan how shell mesh has been created. It controls what it determines as the top and bottom of objects. But I recommend turning it off, especially if you're noticing shell meshing take forever. In terms of the mesher, you can set what the default mesher is. I'd recommend using curvature-based. It is multi-core capable, whereas the other mesh is not. What they call standard mesh is not. And it's much better at addressing complex geometry. What we call the standard mesher is really our legacy mesher. Curvature base is sort of the next generation. I'd strongly recommend it. And then if you're using SOLIDWORKS 2014, if you check out some of these color chart options, there are a couple of new options here to apply different numerical formats to the stress and factor of safety plots. Often if you're bending your model and you're distorting it a small amount, you might see the displacement or deformation as thousandths of an inch or thousandths of a millimeter. And you often want that in a scientific format, times 10 to the power of whatever. But this lets you override that for stress and factor of safety plots. That's been added in SOLIDWORKS 2014. And the other recommendation I make is to use, there's an option down the bottom of the color chart section, use a specified color for values above yield. As you probably know, stress analysis values above yield in a linear analysis are essentially garbage, right? Linear analysis is a great predictor up to yield, but beyond yield, it's not true behavior. And so this just colors that in a gray color so that you know clearly that those values are not real. What it's telling you is the part is yielding. We got you with that. For that to work, all the parts in the assembly have to be made of the same material. Otherwise, it's you get like kind of a mixed scale that can be. There's no way to really express that because different materials have different yield points. But if you've got a part or an assembly with all the same materials, that's a good one to look at. Okay, and so let's pivot over here. We've got a few minutes to take a quick look at SOLIDWORKS flow simulation. So we'll close down what we're working on. We've got two questions that we had come across. We've recently done some flow simulation presentations. So we'll cover a lot of the stuff that's come through, but let's open up a simple flow simulation situation. This is a desktop CPU. It's got some heat generating components inside it. It's got a case around it. One question we have, we've had a couple of times, is how do I analyze just natural convection? I don't want to blow any air with fans. I just want to see this thing in natural convection. And the good news is that is very, very easy. In fact, easier than driving flow with fans or anything like that. So I'm just going to load in SOLIDWORKS Flow Simulation. Like all our analysis tools, integrates right into the SOLIDWORKS environment, so we're never leaving it to go do different stuff. And I'm going to load up a variation of this model. It doesn't have any fans or anything like that in it. If you're doing a natural convection only analysis, a good portion of the heat loss from the object is potentially coming off the case or the enclosure. Right? The outer surfaces of this will get hot as air inside gets hot, and it's going to lose energy to the outside. So what we generally recommend for those situations is to do what we call an external analysis, where we not only model the air and the temperature inside the box, but also what's happening around it. And so then, once we've done that, the question is, how do I turn on, how do I get natural convection happening? It is as simple as checking this box to turn on gravity and make sure it's pointing in the right direction. In this case, the negative y direction downwards as we're looking at it here. So that's all it takes. The only inputs in this model are the heat sources, the things that are getting warm, and some material information, and gravity being turned on. Simple as that. I love when people give me natural convection problems to address. As I make one selection, I apply my heat inputs, I hit run, and I end up with the result I'm looking for. And as we can see here, looking at a velocity profile, what's happening? We have classic natural convection currents forming around this box as it heats up. All right, if we look at temperature, we can see kind of the internal air getting warm. This is a sealed enclosure in this case, but we could also have openings in it and heat rising off the case. So nice and simple. So let's talk about that being simple. What if we have fans? Right, how do we deal with that? One of the primary challenges people have with fans is that there's thousands of fan manufacturers out there, and they have thousands of models that can be run at different rotational speeds. And so even though we supply a good number of standard curves or curves from different manufacturers in the software, there's a good chance that the one you're working with isn't going to be in there to describe that fan's performance. So what do we do about that? Well, we have to come in and create new fan information to load into the software so that you have the performance data for that curve expressed for that fan expressed as a curve. Now, 9 times out of 10, when you're working with the fan manufacturer, they will give you a data sheet. Might look like this, a little picture on it. That's your fan curve. Now we can probably blow that up. Go down and take a look. How do I go from here to here? All right, first time I tried this, I printed this off, I created a grid on it, and I wrote down some coordinates. Here is about 7 by about 0.35. Jot that number down, move to the next point. It's pretty tedious. There's luckily a much better way. It's not a SOLIDWORKS function, but it's a cool little thing that I've found. If you do a Google search for the word plot digitizer, one of the top hits is a little free utility. Let's find that. It's less than a megabyte. And it is a tool that basically lets you import a picture. Right, so the first thing is we've got to create a picture. Great tool in Windows 7 called the snipping tool that I use every single day. Lets you grab a piece of the screen, make it a picture in a couple of seconds, and then you go File, Open, find the picture. If you're looking for a download link for the file, if you go to the Hawker Systems blog, we talk about it on there. You can just search for plot digitizer. It's really simple. You pick the 0, 0 point, and you say that's 0. It's also 0 on the Y direction. You pick a point on here, right? You say that's 50, in this case, cubic meters an hour. Pick a point up here. That's 125 pascals. And then you trace the curve. The one we're after here is this 4 lines. We just pick down, hit done, and you have digitized points that you can copy and paste right into this environment. Just Control-C, Control-V. A couple of things to watch out for when you're creating a fan curve. Now let's create. First of all, there's this pressure drop measured. Static pressure, free blowing, total pressure increase. The trick here is to look at your fan curve and see what the underscore is on the pressure value. In this case, it's delta PF. That is free blowing. You want to make sure those match. The reference density represents the density of the fluid when you took the test. If it was at atmospheric pressure, that's the situation. And lastly, here's the measurement scheme for the flow rate. In this case, we have a volume flow rate, and you can come over and paste your information, making sure the units match. It's a great little connector there. And so, yeah, I'd recommend doing that. Check that out in, it's a write-up on that on our blog if you're interested. Hogriches.com, look for the blog link. So that basically brings us to the end of what we have time for. I got run a little over here. I'm going to attach this PowerPoint to a follow-up email from GoToMeeting. A couple of extra kind of general rules that you may want to check out in there. But here we're looking at our March Wednesday webinar schedule. I have a couple sessions still to go here this month. And so if you're interested in any of these, sign-ups are available on our website under the events section. But lastly, I just want to thank everyone for joining me here today. If you have questions about SolidWorks simulation, we're always interested in your feedback at the end of these sessions. But if you have specific questions, please don't hesitate to contact our support group, of which I'm part. We're there to answer your questions, and we're always happy to walk you through something. I've got my email address there if you have any questions, and I'll stay on the line to see if there are any questions that are sent through the question panel. I apologize for running over time, but otherwise, thank you very much for joining us today, and I hope you found it interesting. We look forward to seeing you in the future. Thanks.